Okay, this lecture's on 16.7, talking about accelerations with relative motion analysis. So before we came up with the velocity of b is equal to the velocity of a plus the velocity of b with respect to a, where this is a translation and this is some rotation. Okay, let's take a look at general plane motion. First of all, let's take a derivative. Take a time derivative. That will give me the acceleration of b is equal to the acceleration of a plus the acceleration of b with respect to a. Now this thing has two components, just like acceleration typically does. We have the acceleration of b with respect to a, and we can give it a vector in the tangential direction, and an acceleration of b with respect to a in the normal direction, and we'll derive what those are. Okay, if we see that the acceleration of b with respect to a in the tangential direction is really just our alpha crossed r of b with respect to a. This would be our vector form. Or we can say it's equal to alpha r if we can do it in scalar analysis. The normal component becomes, what do you think? We could probably, if we knew the velocity in the tangential direction, we could use v squared over rho, but in this unit we're going to see a minus omega squared, and then we keep the vector sign and it points in the opposite direction of the position vector from b to a. So putting that together, we get the acceleration of b is equal to the acceleration of a plus alpha crossed r minus, and go ahead and keep that minus sign, minus omega squared times the vector r of b with respect to a. Alright, so I'm going to go through a couple cases also real quick. The first figure in your book talks about rod BA or AB, and it shows you that it has some acceleration up and to the right, and acceleration of point B is going like straight up. The path of B has a different radius than path of A if they are not parallel. Then that means there's some rotation. So they also give us that there's some omega and some alpha. Okay, if we want to describe the motion, then we can say that this is equal to a translation without a rotation. So here's A, here's B, and these arrows represent the accelerations. So, the acceleration of B and the acceleration of A. It moved to some new point and it has some acceleration. This is the acceleration of A. To get the acceleration of B, we have to consider the rotational motion. So put a plus sign. The rotational motion, A is now our fixed point about which we have some omega and some alpha. A is translating, so we can call it fixed for the rotation. Let's call this r of b with respect to a, and let's go ahead and draw the path of point B. Alright, so if it's rotating, it's gonna have a normal and a tangential component. We'll have a normal component in this direction and a transverse or tangential component. Okay, and if you do vector addition on this, we get an acceleration vector like such. And that's our answer. It's going to be pointed inwards a little bit because it is rotating, and a component of it in the normal direction points towards the center of rotation. We also have, what if we look at a wheel? No, actually, let's look at the same piston crankshaft system that we looked at before, or a similar one. Alright, so let's call this C, let's call this B, and let's call this A, and let's say we have angular velocity omega and some angular acceleration A alpha. Path B, since AB is a fixed distance, is going to be circular. And we can describe B by itself if we just look at AB. The acceleration at B is going to have a component along the path in the tangential direction. We'll just call it acceleration of B in the tangential direction, and it's going to have some normal component also, the acceleration of B in the normal direction. Alright, add those together and you'll get the acceleration. What about BC? Alright, so if AB was going in like this one's going to be doing the opposite. Right? Alpha and omega are going to be counterclockwise in this case. We know in this case that the velocity is fixed, or the acceleration at C has to be going in this direction. It's not lifting off the surface. And we now have a vector over here for the acceleration of B. Alright, then we can describe the motion. If we can, given certain pieces of information, we can extract the rest.